This is my Physics 2211 Lab 3 titled The Black Hole. So I want to give you a brief overview of this slideshow. So there will be two parts. The first part we will be finding the mass of the black hole. The second part is called Don't Crash. In part 1, we are given that a star is orbiting a black hole of an unknown mass and is located at the origin. The star has a mass of 2e30 kilograms, and the position of the star will be generated in the starter code, which will result in a unique trajectory. And in part 2, we're going to use the mass that we found in part 1 to determine the initial velocity the ship can have. This is my Physics 2211 Lab 3 Black Hole. So I want to give you a brief overview of the project. There will be two parts. Part 1, we will be finding the mass of the black hole. We are given that a star is orbiting a black hole of an unknown mass located at the origin. The star has a mass of 2e30 kilograms, and the position data of the star will be generated in the starter code, and that will result in a unique trajectory. Part 2, we will be using the mass that we found in Part 1 to determine the initial velocity that the ship can have without it crashing and still being able to leave the system. We will be creating a computational model for both parts using the fundamental principles that we will cover later. And in our conclusion, we will be asking some what-if questions and analyzing our data. So for our introduction and purpose, in part 1, our purpose is to estimate the mass of the black hole. The system in this case is a planet, and the surroundings is a black hole. Part 2, we will be determining the initial velocity that the ship must have when it leaves the surface of the planet. In this case, the system is a ship, and the surroundings is the black hole. The results that we come up with are that the mass of the black hole is 1.35 e34 kilograms, and the initial velocity of the ship is the vector negative 2.1 e7, negative 4.2 e7, 0 meters per second. So some of the fundamental principles that we will be covering is the momentum principle, which is shown in this equation right here. F net is equal to momentum divided by time, and that's also equal to the perpendicular momentum plus the parallel momentum. The gravitational force is covered in this formula right here. Gravitational force is equal to G times both masses divided by R squared times negative R hat. And then Newton's second law is the position and the velocity update formula. And we will be using all three of these and variations of these formulas and principles in our code. So in part 1 of our computational model, our initial conditions are G is equal to gravitational constant, mass of the star is 2e30, we set delta T, and T is equal to 0, and we start with P equal to mv to find the initial and the final momentums, and then we're finding the change in velocity and momentum, calculating dp over dt, and then we find the parallel change in momentum, parallel force, and the perpendicular force, and then on the top right, we are going to be calculating mbh using the law of gravitation. Here are our results. So we have a resulting magnitude of net force of 8.6 newtons, and then magnitude of parallel components, which is 3.8 e27 newtons, perpendicular component of 8.6 e28, and then the average mass of the black hole turns out to be 1.34 e34 kilograms. So the computational model part 2. So our initial conditions here, bh.m is the mass of the black hole that we found earlier, using the gravitational constant again, and then the mass of the planet, mass of the ship, and delta T is 1, we have all of our initial conditions. And then from there, we first find R, then we find R hat using the gravitational force equation, and then we find F grav. After that, we will use the velocity update formula and position update formula to update velocity and position. And then here are our results. Our initial velocity turns out to be negative 2.1 e7, negative 4.2 e7, 0 meters per second. The closest distance between the ship and the black hole is 1.49 e10 meters. So possible errors could have been attributed towards rounding errors in initial conditions, maybe also because the simulation running time was too short. If it was longer, it would have resulted in a more accurate answer. So what does it mean well, how is the net force and its parallel and perpendicular components different from the rate of change? So as you can see right here, F net is equal to change in momentum over t is equal to the parallel perpendicular forces of momentum, that they are used interchangeably, and they only differ because dp over dt expresses instantaneous change. So for part 2, instead of wanting to take a quick look at the black hole and leave, you decide you want to enter an orbit. So in order to enter an orbit, you need a more circular path, and to have a circular path, you would have to decrease the initial velocity, and that would mean that you would enter an orbit. Thank you for listening.